Greetings, Astronomy 10, and welcome back to your Chapter 3 Part 1 lecture. Today is going to be your one true blue lecture on archaeoastronomy, or the history of astronomy, or the story leading up to how we came to know what it is that we know now. So before I get started on anything that I'm going to say today, let me say that today's lecture is not intended to disparage anyone's religious beliefs or otherwise. It may very well be that science is the answer to how and religion is the answer to why. We are not here to discuss or debate that. What we are here to do is disclose facts. Everything that I'm going to tell you today is a fact. Okay? I'm not here to try to change anyone's perceptions or beliefs. But everything that I'm going to tell you today is true. So let's start with sunspots, shall we? If you look at the first image in today's image bank, you can see that sunspots, although they were largely attributed to Galileo Galilei, Galileo did not discover sunspots. Galileo only discovered sunspots in the same way that Christopher Columbus discovered America, meaning not so much. The Chinese had discovered them thousands of years before Galileo did. Nicholas Copernicus is widely accredited with what we call the Copernican Revolution, or the widespread acceptance of the fact that the sun is at the center of our solar system, that we have a heliocentric or sun-centered solar system. But he did not come up with this idea. Copernicus no more invented the idea of the heliocentric or sun-centered solar system than Thomas Edison invented the light bulb. It was probably Alessandro Volta or Sir Humphrey Davy or even maybe Joseph Swan. Images of all of these old dead dudes are also in the image bank. But suffice to say that there was an ancient Greek who lived just over 2,300 years ago named Aristarchus of Samos. And he postulated that the sun was at the center of the solar system over 2,000 years ago. Now, of course, Nicholas Copernicus had a bunch of research to show that it was probably true, that the sun was at the center of the solar system, and he had a lot of math to back it up. And of course, Aristarchus of Samos had none of that. So this is a bit like comparing apples to oranges. But the fact of the matter is that Copernicus did not invent this idea, right? I apologize. I had a little bit of a mouse difficulty there. We didn't need to send satellites into space to take pictures of the Earth or put spacecraft in orbit to know that it's round, right? We talked a little bit about this last time, that we know the shape of the Earth because of the shape of its shadow that it casts over the moon, right? Sir Isaac Newton, the greatly acclaimed physicist and the human being whose motion we named all of our basic laws of motion after, he did not explain axial precession first. There was a Greek named Hipparchus who researched the matter around the same time that Aristarchus of Samos said that the Earth actually goes around the sun. And there is some evidence that the Mayans knew about it a long time ago as well, due to the what we call the Mesoamerican long count calendar. It's actually kind of interesting. You can Google it if you want to learn a little bit about the Mayans. But also the ancient Egyptians had it laid out pretty well according to how they would position their temples so they could see the precession of the stars. And it's actually thought to be one of the reasons that the pyramids are placed the way that they are. Eratosthenes, once upon a time, came up with the first decent estimate of the size of the Earth. And he did it in a very clever way. We're going to shift the camera just a little bit now. And hopefully this works the way I'm hoping it does. That's not bad. Okay. So what Eratosthenes did is, so here's the Earth. By the way, if you ever see this symbol, the circle with a plus in it, that's the astrophysical symbol for the Earth. So let's say that the sun is here, right? And it's casting a bunch of light. Actually, the sun would be, you know, this huge thing, right? It's much, much larger than the Earth. In any case, it's also very, very far away, but the sun's light, all the light from the sun, all the rays are essentially going to come in parallel to the Earth, right? Because it's so big and so far away. Now, if you're standing here, and there's like a tower or a building or something, and the sun is directly above this point on this certain time of the year, at this certain day, right, at noon or whatever, then that means there's going to be no shadow, right? None whatsoever. The sunlight comes straight down. You've seen this, right? If the sun is directly above something, then there's like no shadow, right? It's just this tiny little blob around your feet, right? But then later on, when the sun is lower in the sky, the shadow is much longer, right? Okay, now on this same day, on a different year, this guy saw that there was a tower, and because it's on a different place on the surface of the Earth on this day, there was a little bit of a shadow. And he measured the length of the shadow compared to the height of the object. And because he knew the distance in between, right, he knew that the shadow pointed this way, right, because the shadow is actually, the sunlight came in this way. And so the shadow is this way. And so this angle had to be the same as this angle. Long story short. And because he knew how far apart these two cities were, he was able to figure out the radius of the Earth. Whoops. And from that, he was able to figure out, you know, the size of the Earth. Pretty clever, actually, right? And so Eratosthenes was the first person to give us our first decent estimate of the size of the Earth. Now, because everybody say hi to Ninja. Ninja, don't knock it over, please. If he knocks it over, I apologize. You know, cats are just going to do what they want to do. In any case, we're making this assumption that all the rays of the sun come in parallel, and actually they come in from different angles from different parts of the sun. And so this wasn't a perfect estimate, but it was pretty good. And it wasn't until, you know, several hundred years later that there was a more accurate estimate for the size of the Earth. Now, Galileo did not invent the telescope. There was actually a guy named Hans Lippershey who came up with the idea of using two lenses in order to try to focus light better. But Galileo was the first one to use it for astronomy. So all of these things, all of these falsehoods, right? All of these misleading points are probably not good places for us to start our study of astronomy, right? Because they're all wrong. So what's a good place to start our study of the history of astronomy to try to lead up to today? Well, let's rewind time about 500 or so years ago. In the West, during this time, the foremost authority over everything scientifically related is the Church, the Roman Catholic Church. And they don't like people like you and me telling what they would have considered essentially crazy conspiracy theories about the way that the universe actually works. If you spoke out against the current model of the universe, which was geocentric, right? Meaning, shoot, I gotta go get the eraser. So if the universe was geocentric, it would mean that, like, the Earth was here at the center, and everything else would go around the Earth. Venus, Mars, and then, this would be the sun. If you ever see a circle with a dot in it, that's the sun. Like, the other planets would be going around the Earth, right? This is the geocentric model of the solar system. And suffice to say that nowadays, we know that it is not accurate. We know that the Earth is not at the center of the universe. We are not at the most special, most important place with regards to anything, really. We're at really no special place in the universe. But the church at that time would not allow anyone to speak out against this model because, according to this model, the geocentric model, the Earth was at the most important place because we were God's creation. And we were the most special and important things in the universe because we made him in his image, and everything else in the universe was supposed to be perfect spheres. All the planets, the sun, the moon, everything were supposed to be perfect spheres moving in perfect circles around us because the universe was perfect and God was perfect and we were perfect, and hooray. And anybody who spoke out against this model, even if they had a good understanding of what was going on, if they did research, and something about their research turned up indications to the contrary, even if they had good scientific reasoning to back it up, the Inquisition would come and pay a visit to them. And if the Inquisition came to pay you a visit, generally you were never seen or heard from again. That was it. And so for a time, religion was ruled supreme over science by fear and violence. But there was a problem. A problem that not even any kind of geocentric model or the church or anyone could explain. And that was a funny thing called retrograde motion. Now, retrograde motion happens, let's say, we're going to redraw this just a little bit here and make it a little more sensical, right? Because obviously the Earth is not at the center, okay? In the middle is what? The sun, right? And so let's say this is the Earth's orbit. And out here, this is Mars's orbit. Okay? Now Mars is actually 1.5 times farther away from the sun than we are. And because it's farther away, it moves more slowly. Now all the way out here, all the way everywhere in the sky, there are distant stars, right? And because we're moving faster than the planet Mars is, right, it's not moving as fast. At some point, we're going to go past it. Now when we're here, it's going to look like Mars is here. When we're here, it's going to look like Mars is here. And when we're in front, it's going to look like Mars is here. And so as we pass Mars, it looks like Mars is moving backwards, not forward like everything else in the solar system moves. Now that doesn't happen all the time, right? It's only when we pass it. For the rest of the time, Mars appears to move forward in the same sense that all the other planets move, in the same sense that the sun appears to move across the ecliptic, in the same way that the moon revolves around the Earth, the same way that the Earth spins, that we move around the sun, and so on, right? Everything in the solar system moves together. But during this time, as we pass the planet Mars, it appears to move backwards. It's not actually moving backwards, it's just moving slower than we are, right? We call this retrograde motion. Now, the drawing that I made here is kind of crude. It's not so great. And doubtlessly, the video that's on today's lecture page will probably show it a little better than I can here. But suffice to say, this is a very well-known phenomenon, and we realize now that this only happens because the Earth is also moving around the sun. Otherwise, this is impossible. Now, they tried to explain this by this crazy thing called epicycles, which instead of the sun being at the center, right, if the Earth is at the center, which we know is not true, and then everything revolves around the Earth, right, that let's say the planet Mars, right, its orbit is anchored here, but it actually goes in a circle around this point on the circle. And so it looks like sometimes Mars will go backwards. And so now instead of a circle, it's a circle on a circle. But these epicycles were never able to properly predict when these retrograde events were going to happen. And so this retrograde motion was a huge problem for the geocentric model, because no matter what they did, they could never beat it into shape such that it would work, such that they could try to prove when it was going to be in retrograde, when they were trying to reproduce results. It never happened. So even the best efforts of mathematicians like Ptolemy were not able to show when this happened. And if you have a scientific theory and it doesn't reproduce results, it can't possibly be right, right? If you have a scientific theory that doesn't work, it's not really much of a theory. Enter Nicholas Copernicus. In about 1510, he wrote something called the Commentariolus, or Little Commentary. It was this little 40-page manuscript about the astronomy observations that he made. And fortunately, because he was really smart and really good at math, he actually made them really accurately, despite the tools of the time, the astronomical apparatuses that one could make were not very advanced. But still, he was able to show that the motions of the planets, including this retrograde motion, were much more easily explained if the sun was at the center of the solar system instead of the Earth. Makes a lot of sense, right? So this was based on 7 very basic assumptions, and they're written in a really kind of funny way. But the first one is that there is no one center of all the celestial circles or spheres. And what that was supposed to mean is that if the sun's at the center here, and then there's other planets, then as they all move around, the center of gravity of the solar system kind of moves around a little bit. And that's true, because, you know, there are planets that are really far away, right? And so the center of mass between, say, the sun and Uranus is far outside the sun, and you have to add up all of everything in the solar system to figure out where the center of mass of the entire solar system is. Anyway, the center of the Earth is not the center of the universe, but only of gravity and of the lunar sphere, meaning that we are all held down to the ground because of Earth's gravity, and the moon revolves around us, right? Number 3, all the spheres revolve about the sun as their midpoint, and therefore the sun is the center of the universe. It's actually only the center of the solar system. We know that now. Number 4, the ratio of the Earth's distance from the sun to the height of the firmament, or the outermost celestial sphere containing all the stars, is so much smaller than the ratio of the Earth's radius to its distance from the sun that the distance of the Earth to the sun is imperceptible in comparison to the height of the firmament. What that really means is the distant background stars are so far away from us that we can't compare it to the distances across the Earth or from the Earth to the sun or so on. But he was kind of wrong. We've actually been able to measure the distance from the Earth to the sun, right? Whatever motion appears in the firmament arises not from any motion of the firmament, but from the Earth's motion. Stars rising in the east and setting in the west happen because the Earth rotates. Oh, there goes Ninja. Ninja, what are you doing? I'm teaching a class. Ninja, come here. Come here. Come here. Okay, well then I'm going to turn this back. Ninja. Come on. Come on, Ninja. Oh, I got a ninja. Oh, I got a ninja meows. Everybody see the ninja meows. What's the matter? Hi, everybody. This is a huge dork. His name is Ninja. Okay. Number 6, what appears to us as motions of the sun arise not from its motion, but from the motion of the Earth and our sphere, which will revolve about the sun like any other planet. The Earth then has more than one motion. And that's true, of course. Not only does the Earth rotate, but it also revolves around the sun, and the direction of the Earth's axis precesses, right? Every 25,000 years or so. The apparent retrograde and direct motion of the planets arises not from their motion, but from the Earth's. And that is true. Remember, as we pass Mars and its orbit, it appears to move backwards. And that was pretty good. And so from these very basic assumptions, he was able to show that he could predict when retrograde motion was going to happen. And that was unheard of. Nobody had ever done that before. Now, he wrote a book about heliocentrism, and it was a lot more detailed. It was called On the Revolutions of Heavenly Spheres. Of course, it was published in Latin, I think. But by the time it was finally published, because he didn't want to publish this book, because he was always, wary that he was going to get a visit from the Inquisition. And so he did not want to publish this book. And as a matter of fact, he did not publish this book until the year that he died, because he was so afraid of the consequences. Oh, Ninja. He was very fearful of official church criticism. At one time, he received a letter from the Archbishop of Capua, and it read, "Some years ago, word reached me concerning your proficiency, of which everybody constantly spoke. At that time I began to have a very high regard for you, for I had learned that you had not merely mastered the discoveries of the ancient astronomers, uncommonly well, but had also formulated a new cosmology, or a story of how the universe came to be. In it you maintain that the Earth moves, that the Sun occupies the lowest and thus the central place in the universe. Therefore, with the utmost earnestness, I entreat you, most learned sir, unless I inconvenience you, to communicate this discovery of yours to scholars, and at the earliest possible moment to send me your writings on the sphere of the universe together with the tables and whatever else you have that is relevant to this subject." Needless to say, he did not. And if you were Nicholas Copernicus and the church wrote to you saying, "Hey, send us all of your blasphemous stuff," would you do it? Yeah, I wouldn't either, because I don't want the Inquisition coming to my birthday party. And instead, he waited until it was almost too late for him to see, and the result was this thing we call the Copernican Revolution, or the paradigm shift that accepts heliocentrism, or the fact that the sun is actually at the center of the solar system and not the Earth. Enter Tycho Brahe, who was the equivalent of, I don't know, some gross, growy frat dude. If you look at the image of him in the image bank, one need look no farther to see what kind of privileged douchebag this guy was than his necklace. And you can see the elephant on the necklace, that marks him as a member of the Order of the Elephant. It was a very exclusive order, generally only about a dozen or so members at any one time. They're the richest people in all of Denmark, and the leader of this order was the king. That's how rich this guy was, okay? He was also an astrologer and an alchemist, both of which are not real things. and not much of a mathematician. And he was so bad at math, in fact, that one time at a party he got into an argument with a fellow gentleman scientist, because back then the only people who could afford to try to do science were people who were rich, right? Um, and so he got into an argument with another gentleman scientist, and neither one of them were good enough at math to disprove the other person. And so they got into a big argument, and they had to both leave the party in a huff because, they were killing everybody's vibe. And when they ran into each other at another party sometime later, they settled it in the only way that two gentlemen scientists could, with a duel, with swords. And that's why, also in the image bank, there is an image of Tico's nose. That'll be on the exam, by the way. He got his nose cut off and he had to wear a metal nose for the rest of his life because not only did he suck at math, he sucked at sword fighting too. But he was rich, filthy rich. So rich that he had this huge, what they call an astrolabe, which was basically a series of rings in like a big enclosure or, like a rooftop kind of thing, that you could look out under the stars. And he used that to mark the positions of objects in the sky. That was the best thing they had because back then they didn't have telescopes. But of course, just because you have a bunch of money and you can build things doesn't mean you know how to use them, right? Enter Johannes Kepler, the guy with the beard and the big, goofy, frilly collar thingy. Kepler worked under Tycho Brahe at his observatory, and that allowed him access to this equipment, and so he was able to figure some things out. He was also very religious, unfortunately, and so Johannes Kepler barked up a few wrong trees, and one of them is pretty fantastically funny. I'm going to share this with you now. Not funny in the ha-ha sort of sense, but funny in the, oh my god, people actually thought this kind of sense. So what Tycho Brahe believed, or excuse me, what Johannes Kepler believed about the solar system and the placement of the objects in the solar system went something like this. There are a series of what we call perfect solids. There's the one with the lowest amount of sides is a triangular pyramid. This thing, right? We call this a tetrahedron. The one with 6 sides is a cube, of course. We all know what a cube looks like. And then there's one with 8 sides, what we call an octahedron, and it has sides that are equilateral triangles. And it's a little difficult to see. And if I hold it up a little bit, right? We've got equilateral triangles. It has 8 sides. There's the dodecahedron, which has pentagonal faces, and it has 12 of them. And then there is this thing called the icosahedron, which has faces that are also equilateral triangles, but there are 20 of them. Now, of course, I only know all of this because I play way too much Dungeons and Dragons. Imagine that, guys. Your physics professor is actually a nerd. Oh, I'm sorry, your astronomy professor is actually a nerd. Okay. Now, what Kepler thought was that if you took, say, the pyramid, right? The equilateral triangular pyramid, the tetrahedron, and you drew a sphere around it, right? Say the sun here was in the middle. This was supposed to be like the radius of Mercury's orbit, right? And then you drew a cube around that, and you drew a sphere around that. That was supposed to be the radius of Venus's orbit. And then you drew the octahedron around that, and drew a sphere around that. That was supposed to be the radius of Earth's orbit, and so on. And it was a neat idea and all, but it was wrong. And he spent a lot of time barking up that tree because he thought that the universe had to be made up of perfect solids because he was also very, very religious. Not terribly unlike uh, Tycho Brahe and many people before him. But fortunately, he was also very good at math still. And so he was able to prove beyond the shadow of a doubt that the shape of the planet's orbits were ellipses, like ovals, and not perfect circles. We'll revisit this issue probably next time when we talk about Kepler's laws of planetary motion. But he also discovered a very, very bright star. But since he used Tycho's observatory to find it, even today we call it Tycho's supernova. This happened in 1572, and there are a couple of images of it in the bank, in the image bank. In the first one, it's sort of the red blob up in the upper left corner, and then the other one that's more brightly and more multicolored, it's largely like green and sort of orange up at the top with purple around the edge. That's taken in the X-ray portion of the electromagnetic spectrum. Suffice to say, back at the time, it was real, real bright because a star blew up and went supernova. Even hundreds of years later, it's still pretty bright. Enter Galileo Galilei in 1610, the famous mathematician and physicist, the man who figured out that two cannonballs of unequal mass fell at the same rate from the Leaning Tower of Pisa. The man who realized that it's only air resistance that causes feathers to fall more slowly than hammers. And the way that he did that was he took like a big bell jar and pumped all the air out of it. And then a feather and a hammer fell at the same speed. He also figured out that the acceleration of Earth's gravity pulls everything downward and continues to accelerate things by rolling balls down ramps. And finally, most importantly, because this is not a physics class so much as it is an astronomy class, Galileo took the telescope and turned it toward the heavens in order to see what he could see out there in the universe. Now, what do you suppose he saw? I'll give you a big hint. He saw a lot of things that the church wasn't going to like. So, one of the things that he saw were moons orbiting the planet Jupiter. Ganymede, Callisto, Io, and Europa, what we call now the Galilean moons, because Galileo discovered them. Now, according to the geocentric model, the old Earth-centered model of the universe, everything was supposed to be perfect, the Earth was supposed to be at the center, and everything was supposed to move in perfect circles, and everything goes around the Earth, right? But here we now have 4 moons that are very clearly orbiting Jupiter, and not us. Is that a problem? Well, it goes against the old model, right? The church probably wouldn't like that very much. He also saw sunspots. Now that's not new, right? The Chinese saw them thousands of years ago, but Galileo was very clever in that he would look up at these sunspots and plot their positions. Draw them like a map on the face of the sun. And then he'd go look, several hours later, a day later, 2 days later, and track their movements across the surface of the sun. He realized a couple of things. For one, he figured out how long it takes for the sun to rotate, which is about 2 weeks or so near its equator and closer to a month closer to its poles. But what does that mean? That also means the sun rotates differentially, meaning it rotates faster at the equator and slower at the poles. Why was this a problem? Well, that proves that the sun is neither static and unchanging, nor is it perfect, right? Because it's not even spinning at the same rate. It's not one solid object. So that's a problem. He also saw that as the planet Venus orbited the sun, that it exhibited different phases, like the moon does. Now, because the planet Venus's orbit is tilted ever so slightly relative to ours, when Venus is at what we'd call its new phase, it's actually lit just a little bit at the top. And then, if it's at its full phase, it's bright, but it's much smaller looking, right? Now, this set of configurations, as evidenced by the image in today's image bank, is only possible if Venus orbits the sun and not us. That's also a problem, right? Remember, everything is supposed to orbit us. We're at the center of the universe. Finally, he pointed... Oh, actually, there's a couple more things. He pointed his telescope into the Milky Way, and what do you suppose he saw? What's in the Milky Way? Stars, right? Millions and millions of them. Billions. And so it became obvious that when Galileo looked into the band of the Milky Way, that some stars were farther away and some stars were closer. That's also a problem, right? Because everything is supposed to be affixed to this distant firmament sphere, right? And so things on this sphere aren't supposed to be closer or farther away. Finally, he looked at the moon, which, you know, even with the naked eye, you can see some of this detail, but with a telescope, if you've ever looked at the moon, you can see a lot of stuff. Craters and what they call the seas, the mare, right, which are big flat areas. You can see mountainous ridges and so on, right? And that, for that to be there, for those craters and those mare to be there, that means that the moon is not some kind of perfect object, right? This perfect object, this static and unchanging object does not exist, right? The moon is not that. We'll talk a little bit more about why the mare exist. You know, preview of coming attractions is when an asteroid or a meteor, you know, crashes in through the surface plate and volcanic material spills out. But that can't happen anymore because the moon is now volcanically dead. Anyway, we'll talk more about that when we come back to the moon in the coming weeks. But suffice to say that the moon is neither static nor unchanging. And so we've got the Galilean moons, sunspots, the Milky Way, the phases of Venus, and the moon, right, not being perfect. And so we have all of this evidence against the geocentric model, to say nothing of Copernicus's evidence about retrograde motion, and also what do you call it? Not Nicholas Copernicus, Johannes Kepler's proof that all the planets move in ellipses. So now there's all of this evidence, right? And the church is starting to feel the pressure because science has spoken. Now Galileo wanted to take all of these things that he found and put it into a book and publish it. And that was going to be the last nail in the coffin. And the Pope, who was actually a friend of Galileo's, said, no, you can't do that. You know what kind of what kind of position that's going to put me in? It's going to make me look real bad. We're all going to look real dumb, and I can't stand for that. Okay, so don't do it. And so Galileo was told that if he was going to write a book about his findings and his evidence and all that, he could do it. But he had to present both theories, right? The geocentric and the heliocentric together. And not favor one over the other. He had to show that both of them were kind of the same, right? And so he wrote his book, The Dialogue Concerning the Two Chief Systems of Worlds. And when he did so, he did not listen. He wrote the book as a dialogue in between two friends, Salviati, the learned academician, and Simplico, the follower of Ptolemy and Aristotle. Now, if you speak Italian, or indeed any Romance language, like Spanish or French, Portuguese, etc., you can probably put together that Simplico means that he wrote this character as a simpleton, an idiot, right? And as a matter of fact, Simplico, not only did he slur his speech and stutter, he made terrible, incomprehensible arguments, and he even looked and sounded like the Pope. Needless to say, Salviati absolutely destroys Simplico in every argument that they have, and Galileo presents all of his evidence for the heliocentric model quite elegantly, such that even people that were not learned in astronomy could understand it simply. And what do you want to guess what happened after that? Yeah, the Inquisition came to pay him a visit. Now, because the Pope and Galileo were friends, the Pope came to see him after he was arrested, and he said, "I told you can't do that." But Galileo was able to talk him out of, being drawn and quartered, or, you know, murdered in some other kind of incomprehensibly painful way. And instead, Galileo was allowed to live out the remainder of his life on house arrest. Which is not so bad, because honestly, he was pretty rich. You know? He got to live the rest of his life out in this beautiful Italian villa, which kind of like overlooks this, I think it overlooks like a mountainside. Like it doesn't get any better than that. So he was on house arrest, but people could still come over to visit him. It wasn't so bad. But he died, and the book was published anyway, and eventually the world at large has come to realize his contributions, and people were able to build their own telescopes and reproduce his results. So the church couldn't hide the truth for long. Now, he had a lot of followers. He had a lot of friends, and he had a lot of people who were very unhappy about the way that he was treated. So much so that if you look at the very last image in today's image bank, you will see a chalice with a bone in it. That bone is a finger bone. Now, if you were one of Galileo's followers and you wanted to exhume one of his fingers to put on display, to send a message to the church, which finger would it be? Yeah, it's his right middle finger, everybody. And that is on display in perpetuity in the museum near Galileo's home. Okay. That is your one true blue lecture on the story so far, or the story leading up to modern astronomy, where we will begin our study of the universe in earnest together. So, if you have any questions about today's material, please get a hold of me through the normal channels. If not, please make sure you study up on today's material for the quiz next time. And I hope you have enjoyed today's lecture as much as I have had giving it.